In the last video, we saw that if you have an algebra of functions, you can define the linear span of these characteristic functions, and they will give you something we call a function algebra or algebra of functions. That's basically a vector space with a pointwise multiplication map. And now we're going to introduce this notion of simple functions. If you've taken 450 again, you probably saw this already, and this is really the same definition, except we're working with a general measurable space. So let's let xa be a measurable space, and a function, we call it a simple function if it's essentially a linear combination of some characteristic function from this a. So here, simple means I can find finitely many of these an's. So notice I put a fixed n here, so it's finitely many of these an. They're all coming from the sigma algebra A. And then you can find some scalar alpha I in R. So here I'm only deal with real value functions. If you like complex value function, you'll probably need the alpha I in C. So this F is essentially the linear combination summation of these alpha I times the characteristic function of each of these an, I should say alpha n. All right. So we saw simple function is basically form an algebra of function from last class, and also we had a remark in the last video says if you have a sigma algebra, or in fact you only need an algebra, then you can always pick these an to be disjoint. Okay, so you can always assume you can pick these an to be disjoint sets. If otherwise, you can always kind of break them into disjoint subset, and you can do the linear combination that way. All right, so the goal of this video is to prove the main result of this section is essentially showing every measurable function is a limit of these simple functions, and a limit in a very nice way, all right? So I'm going to state the main theorem. This is the main result we are trying to prove in this video. So essentially it's saying if I have some measurable function, so here I take a positive, non-negative measurable function that takes value in 0 to positive infinity, I allow positive infinity. Again, measurable here, it just means Borel measurable, where you equip the 0 infinity with the Borel sigma algebra. Then all the measurable function, I can show that they are actually approximated by simple functions. What I mean by that is that I can always find a sequence of simple functions. Let's call them phi n. It's phi n defined from x to 0 to positive infinity. I don't need to take infinity here. And it will satisfy two properties. So first of all, these phi n of x is always increasing. So I take any x, the phi n plus 1 of x is always greater than or equal to phi n of x. And actually, I can make them to be always bounded above by this f of x. Okay, so you also have this side. And the second, these phi n of x will converge to f in a pointwise sense. So you fix any x, these phi n of x will give you the f of x in the limit. And this convergence, well, usually you don't have uniform convergence, but if you only look at those n where f of x is bounded by this number n, so n is fixed here, then if you just look at this function on this very specific set, then your convergence is actually uniform convergence. Okay, so this is last part. All right, so for the proof, you probably already seen something really similar when you took PMATH 450, or you will be taking PMATH 450. And you will see this somewhere in that course. And the proof is really pretty much the same. Okay, so if you replace this x by the real line, then you get the same proof. So I just want to briefly talk about the proof idea, and I'm not going to fill in too much detail. So the idea is the following. So first of all, because your function is measurable, it can take value from 0 to positive infinity. It can take a lot of values, so you want to do the approximation in 2 steps. Okay, so where each step you want to achieve 2 goals. So first of all, let's say in step the nth approximation. First of all, you want to catch the value on a larger and larger interval. So you want to approximate all the f where f of x is less than or equal to n, for example, all right? So essentially, I'm saying vertically, the magnitude of f, in each step, you need to approximate a larger value of x. And second, you also, because you're doing approximation, you need to have a finer and finer approximation. So you need to have a finer approximation. What do I mean by that? Is essentially you want to approximate well, so up to, let's say, something like 2 to the negative n accuracy. Okay, so let's say up to 2 to the negative n accuracy. All right, so as we go over the proof, you will probably see what do I mean by these two goals in each step, okay? So usually you really can't ignore this part one because your function is really large. You cannot just jump in and define a phi n that's approximate everything up to 2 to the negative n accuracy because sum f is really, really large, okay? So that's kind of the idea. So so for this, let's fix an n, and I want to define a bunch of sets. So I remember the first goal is that we only need to worry about the functions between 0 and n. So and we need to chop it up into intervals of size 2 to the negative n. So for every, that's giving me how many intervals? Well, k can go from 1 to n times 2 to the n intervals. Okay, so so for example, when f of x is between 0 and 1, you want to chop into 2 to the n of them, and 1 to 2, you chop into 2 to the n again, and so on. And you can only do n of them. Okay, so you end up with n of these 2 to the n intervals. And that give you a finite. Remember, we need to have a finite collection of in the simple function. So we can just do n goes to infinity. We cannot approximate everything. Let's end at fx equals to n. Okay, so let's define n times 2 to the n interval where each of these a, k of n is essentially my function where this function is between, let's say, k minus 1 over 2 to the n. And I want to make them disjoint, so let's make the left open and the right, left closed and right open. Okay, so I will make a k of n equal to that. So let's also define the whatever that's left over. Let's call it Bn. Okay, so Bn is x take away of all the a, k, n, where k going from 1 to n times 2 to the n. Okay, so that's essentially all the x where the f of x is really large, is greater than or equals to n. Okay. All right, so what do I do with these sets? Well, I need to pick a simple function to approximate on each of these collection akn. And by the way, you may notice all of these are in the sigma algebra A because the function f is measurable. Okay. All right, so let's now write phi of n of x. I want to make this phi of n, remember I want to make it less than or equals to f. Okay, so this is, I want to make it something extra. If you follow Ken Davidson's notes, he didn't require that, so it's a little bit easier. He used the right endpoint. Because I want to make it less than f of x, so I need to pick the minimal value on this interval. So I have to make it equals to k minus 1 over 2 to the n. That's my function value on a kn. Okay, so here k going from 1 to n times 2 to the n. And I also have another value, which is bn. So how about let's make it, well, b is everything that's greater than or equal to n. So let's use the minimum value. Let's just say n times chi of bn. Okay, so this is a finite collection, a finite linear combination of characteristic functions. So this is a simple function. All right, so I want to claim that this collection of simple function works. Okay. All right, to show that, so let's prove the first thing. So I want to show the phi n of x is actually increasing and bounded above by f of x. So for every x, and you can probably already observe that phi n of x is less than or equal to f of x. That's just trivial, is because on each of these a, k, n, we're picking the minimal value. So we're really picking something smaller than f of x. So that's trivial. And I want to compare phi n of x with phi of n plus 1 of x. And you may notice if I consider a and k, where, or I should say kn, where that's basically all the x, where k minus 1 over 2 to the n, that's equal to f of x, strictly less than k over 2 to the n. Well, this is related to a of k, well, 2n, or actually I should say 2k 2n. So how do I see that? Well, I can raise the power of the n by 1. So if I raise it by 1, I'm basically multiplying 2 on both top and bottom. So this should be 2k minus 2 and 2k. Okay, so this is essentially what this set is. And based on that, you can say, well, this is essentially the 2k minus 1 n plus 1 union a of 2k n plus 1. Okay, and this is really a disjoint union. You may notice all these AKN, they're disjoint. They're the pre-image of f of some disjoint subsets. So they're all disjoint. And you can see this AKN is really the union of these two. Okay. All right, so let's consider what the phi n of x can be. So there are really two cases. Well, if f of x is greater than or equals to n, then the phi n of x, by definition, well, it just comes from the set x is basically in Bn, so phi n of x equals to n. And you can convince yourself in this case, the n plus 1 of x, well, depends on how large f of x can be. If f of x is greater than n plus 1, then phi of n plus 1 of x is n plus 1, and you have n less than or equal to n plus 1. Otherwise, the phi n plus 1 of x will give you some value that's, of course, has to be greater than n. Okay, so that should be quite simple. And otherwise, this x has to be contained in some akn. So let's just say x is inside akn. Then the phi n of x is equals to k minus 1 over 2 to the n by our definition. And this akn is the union of these two, 2k minus 1 n plus 1 and 2k n plus 1. So there are two possibilities of phi n plus 1 of x. It can be either coming from the first interval, which should give you a value of 2k minus 2 divided by 2 to the n plus 1, or it comes from the second one, which gives you the value of 2k minus 1 divided by 2 to the n plus 1. Well, the first one is essentially the same as what we had before, that's k minus 1 divided by 2 to the n. And the second one is just slightly larger than the first one by 1 over 2 to the n plus 1. So in either case, you can convince yourself the phi n plus 1 of x give you a larger value. Okay, so you really have an increasing sequence of simple functions. Okay. And now let's consider the second part. I want to show that this limit of, okay, so where's the second part? I want to show that the pointwise limit of phi n of x is equals to f of x. Okay, so let's prove that. So first of all, I want to show something. So if the for every x such that f of x is less than or equal to n, you can see that by our definition, the f of x needs to be between some value of these 2 to the something, well, k over 2 to the something. So let's say x is inside a of kn. So f of x minus the phi n of x well, this is just equals to the f of x minus k minus 1 over 2 to the n. And this f of x is, because x is inside this akn, well, is greater than or equal to k minus 1 over 2 to the n, but less than k over 2 to the n. So it's inside this small interval of the length 1 over 2 to the n. So the f of x minus k minus 1 over 2 to the n is at most 2 to the negative n. Okay, so this is at most 2 to the 1 over 2 to the n. Okay. All right, so because of that, so for such x, so if f of x is finite, if f of x is less than infinity, then it has to be less than or equals to some n, and for n large enough, the f of x minus Pn of x is less than 1 over 2 to the n. Okay, so f of x minus Pn of x will be less than 1 over 2 to the n for large n. And that's essentially saying if I take the limit n goes to infinity of Pn of x, I'll get f of x. Okay, so they're really close for large n. That means the limit converge. And I just need to do one more thing. If f of x is equals to infinity, I'm allowing f of x to take value infinity. So in this case, the x is really inside Bn for all n because f of x is really large. So from our definition, Pn of x is equals to n. Okay, and because it's equal to n, as n goes to infinity, that converts to positive infinity, which is the value of f of x. Okay, so we do have a pointwise limit. And finally, I want to show that if I just focus on one collection of sets, so if I only consider all the x where the f of x is less than or equal to, say, some big N for some fixed number n, then the convergence is really a uniform convergence. And to convince yourself that, let's just take for every n and m greater than, let's say, the same n. Okay, so how do I know this sequence is uniform convergence? I just need to show that there's some uniform bound of these phi n of x and phi m of x. Okay, and you can convince yourself the following. So I can use triangle inequality. I'll just make it a little bit bigger. Is the difference between phi n and this phi m of x minus fx. And each of them, these phi n is the nth step, so its accuracy is 2 to the n, negative n, and phi m is accuracy 2 to the negative m. Because I am on this set, so I know f of x is less than or equal to n on here, so this x is never inside bn or bn in any case. So I have a good approximation. So you can convince yourself this is less than or equal to 2 to the negative n plus 2 to the negative m, but when n and m are greater than this big N, is at most 2 to the negative n, let's say 2 of them, so this is plus 1, okay? All right, so because of that, this phi n is some Cauchy sequence, and the convergence is uniform. Okay, so phi n will converge to f uniformly. Okay, so let's finish the proof of this proposition.